Okay, please go ahead.
Okay, thank you, Professor Wang, for the introduction. Today, I'll introduce a remote sphere method to solve Poisson equation in full potential KKR. In principle, people can solve the Kohn-Sham equation to get an electronic structure for a solid. Here, psi is an eigenfunction, epsilon is the eigenvalue, eigenenergy. The effective potential is the summation of Coulomb potential, exchange coordination potential, and external potential. The external potential is known. The exchange coordination potential can be computed by some functional. So what left is the Coulomb potential. To solve this equation, people can pick up some basis and expand the eigenfunction in terms of the basis. Then people can solve this equation self-consistently. One popular basis is the plane waves. It can accurately to solve a system, but it requires a large number of bases. For example, more than 10,000 plane waves is required. So this can cause trouble in some complicated system and some application. For example, if we want to calculate the dielectric function, it is pretty slow because of big matrix diagonalization. One replacement basis set is the Slater type orbitals. This can reduce the order of basis by like 2 order of magnitudes. But it's not accurate as plane waves, so it cannot be used to do structural relaxation. Another method to solve the Kohn-Sham equation is that we can solve the system's Green's function while multiple scattering theory. This is called KKR. The method, one advantage of the method is that it separates the single set scattering from underlying structure, and it can also adopt the coherent potential approximation to deal with disorders. Defects. This for this kind of system, it cannot be done by the wave function method. For both methods, it requires self-consistent. It means that people need to solve the new for each iteration, people need to solve the charge density, and from the new charge density, solve the effective potential. So the external potential is known. The exchange coordination potential can be calculated by functional. I'll focus on how to solve the Coulomb potential for this. In KKR, the charge density can be obtained by the imaginary part of the Green's function. The way to solve the Coulomb potential highly depends on how we model the crystal. Say if we model the crystal by non-overlapping atomic spheres, the charge density inside the sphere is spherical, and the interstitial charge density is constant. So we can add some constant into the sphere and then remove it. So it can be treated like this. The charge density, the potential inside the sphere can be calculated by equations similar to this one, and the constant charges contribute a modern term. So for ASA, it's pretty easy. But if we divide the system by non-overlapping Verona polyhedron or some arbitrary VPs, it's kind of difficult to solve the Coulomb potential term. People used to solve this by expanding the 1 over R prime term by this equation, if this condition is satisfied. And then further expand.
Can I just ask a question here?
Sure.
So spherical harmonics is a basis of functions in the spherical coordinates, but when my understanding is that the charge density within your sphere is not spherically symmetric, right? It has the symmetry of the crystal because of the crystal fields and so forth, right?
Yes. In atomic sphere approximation, the charge density is spherical. It is spherical, but it has the symmetry of this system.
Sorry, I'm confused. If it's spherical, then you don't need spherical harmonics.
Oh yeah. For this one, it doesn't. This is a general solution if we expand this 1 over r minus r prime term by the r small and r bigger.
Okay.
This is a general one. So if we use it for the ASA calculation, then it has only L equal to 0 term.
Okay, but in general, the charge density is not spherically symmetric.
Right.
But it can have a symmetry of the lattice. So, to capture this angular dependence of the charge density, one may want to, instead of using spherical harmonics, you can use other things like cubic. For example, if you have a cubic type of lattice,
yes,
you can use cubic harmonics and things like this. So, what do you think of that?
Yes, we can use cubic harmonics, but if we use cubic harmonics, say for a BC system or BCC system or FCC system, you can only have L equal to 0 term, L equal to 4 term.
Mm-hmm. So, that may simplify. I mean, you may get fewer terms because my point is that if the charge density has a certain symmetry of the lattice, maybe one can take advantage of that in defining the angular basis.
Yes, we can take advantage of that.
Okay, thank you.
Okay, so if we expand these terms,
I think part of the point is that you want codes and methods which are generally applicable. You don't want to have to go around picking this, that, and the other. If you solve these equations properly, then and that is what the answer is, and there's no argument anymore, right? And there's no fussing because some structure has got something has got an odd structure.
Mm-hmm.
Mm-hmm. Okay, may I go on?
Yes, go ahead.
Okay, if we insert these two expansions into the Coulomb potential, after some manipulation and group the terms, then the final Coulomb potential can be calculated by these equations. Please note that in these equations there are multiple nested L sums. This is caused by these two expansions, and this nested L sums needs large L cutoffs. Another thing is that for the first expansion, it requires this condition that R must be smaller than R prime plus R. Can this condition be satisfied in the whole space? Of course, it's not. Say, for example, for the points inside the moon region, say in this region, that condition is violated. So people need to put together some correction term. It is also called near field correction. Gornish proposed that the near field correction term can be derived by adding a B vector to the denominator and remove it. Then by some manipulation, they obtain the near field correction by these two equations. This equation is highly sensitive to the B vector, the pickup of the B vectors. Gornish proposed that the B vectors can be chosen to be the SRR prime direction. But Witters proposed that this B vector should be depend on the radius of the bounding sphere. But no matter which option you use, this near field correction is conditionally convergent. So it's not so so good for real calculation. There is one removed field method was proposed in 2002 by Nichols and Shelton. They based on two observations. The first is that if the Coulomb potential is calculated by extended charge density, it should be of this form. If we calculate the potential near for the point near the origin, it can be obtained by the truncated charge density, and these two methods should be equivalent. Equate them, they obtain the coefficient A, L, and then the final Coulomb potential can be obtained by this equation. So this needs some L max for the multiple sum, and it also needs a shape function. So shape function and the multiple sums needs like a large cutoff for the L. This method was reformulated by Aftab et al. By in around 2011. They based a similar observation, but they write the equation differently since they adopt the isoparametric integral. The first observation is that by extended charge density, the Coulomb potential should be of this form, and inside the R mean region, they write the Coulomb potential by this form, the intercell contribution by this form, where the coefficient AL is given by this equation. So equate these two solutions, they found a near field correction. Please note that in their equation, this integral range is incorrect. I will explain this later. And this near field correction is actually obtained by this term and this term here. Their result, they tested their result by, this is the isoparametric integral that they used. They divide the VP into several pyramids, and then flat the by the inscribed sphere surface to a plane, and then distort this part to a cubic. They sample points in this cubic and map it back to the pyramid. All these are related by Jacobians. They test their method by Morgan model. This table shows their result. It agrees pretty good with the exact solution, except for L equal to 0 and M equal to 0. This is because that they use the direct sum for this coefficient AL for this R sum. When L equal to 0, this R sum is slowly convergent. So it must be done with ever sum. And another thing is that they use different Gauss mesh to obtain accurate result compared to the exact one. This is not so practical when applied to real system. I also tested this one with a real calculation. It works good for a high symmetry system like a BCC or FCC system. But if the system has symmetry breaking, it causes trouble. For example, say we have a niobium, a BCC niobium. If we move the central atom along x-axis by a little bit, this system can no longer have the TD symmetry. The symmetry breaking causes the shear of neighbors breaking. Say for the first shear, the nearest neighbors, they have 8 atoms, 8 sides. Because the symmetry breaking is split into 2 subshells, 4 atoms in each subshell. Similar thing to the second subshell, it is split into 4 subshells, and the seventh shell is broken as well. Because of symmetry breaking, the A11 term appears. This term should be welcomed since it contributes to the force calculation. this column shows the result if we summed summed up to different shell cut off. Say if we cut off, say if we sum up to the first subshell, the result is 1.118. But if we sum up to the second subshell, the result is 0.081. This is because these two subshells has a similar contribution, but with the opposite sign. So they have cancellation. So so let's look at this column. We can say that if we pick up a wrong cutoff, we can get a very wrong result for this A11 term, and the fourth is incorrect as well. And the converged result should be this one. This error is calculated relative to this converged result. So to solve this problem, I reformulate the result by error sum for the intercell part. This is the intercell part. It has an R sum. This R sum can be done by the error sum by these equations. And inside the R mean region, the intercell part should be of this form. If R goes to 0, this one is still valid. And these terms can be expanded into this form. So by expanding these terms and group the terms, I obtained that the coefficient AL by this equation. For the near field correction term, remember that this is the solution obtained by the extended charge density, and this AL is obtained by truncated charge density. So by equating these two solutions together, so the near field correction is obtained by this one and this one. The old near field correction was given by this equation. Remember that this is derived by this term and this term. It should be integrated up to the bounding sphere. Another thing is that inside the VP, the truncated charge density is equal to the extended charge density. So we can simply we can get the near field correction that should be integrated from the surface of the VP to the bounding sphere. So this is the correct one. I tested my equations by the Zhenhua model. Zhenhua model is a lattice of positive ions surrounded by a homogeneous electron charge density. For the Zhenhua model, the Coulomb potential and the Coulomb energy are given by these two equations. If I use removed sphere method to calculate Coulomb energy, it is given by this equation. Here, Vm is the generalized Madden potential. The Vm0 can be calculated by the dirichlet boundary value problem, and it's given by this equation. I plotted the FCC Zhenhua model in this picture. The black line is the analytical result. I plotted my RSM result with different Lmax. For Lmax equal to 0, this is the red line. It deviates from the analytical result. If Lmax equal to 4, it agrees much better. But if Lmax equal to 6, it agrees pretty well for this range, but it still has deviation here. If Lmax equal to 8, it agrees exactly with the agrees pretty well with the exact result. I also calculated this with the BCC Zhenhua model, similar behavior to the FCC result. For the Coulomb energy, I can calculate the Coulomb energy with our removed sphere method, and compared to the exact one, it has a pretty small deviation.
So
Another
do
test
you have any? Sorry, do you have any idea what exactly is the functional form of the convergence with respect to Lmax? I mean, does it converge exponentially, or how? I mean, what's the how the error say at X point? How does it depend on L? I mean, do you have some estimate, understanding, some feeling for this? You know, what exactly? Why is it that exactly at 8 it works, and then is there some way to understand this somehow physically?
I have some pictures later. We can show that with why Lmax. That's for the near field correction. If we don't have the near field correction, we cannot get the exact agreement here. Let me answer the question later. Let's check the Morgan density. Morgan model is a virtual system which has only electronic charge density. It is given by this equation. Here, Tm are the shortest reciprocal lattice vectors. The Coulomb potential is given by this equation. If we expand this equation and write it in this form, we can get the analytic coefficient alpha L. This is the counterpart to the AL plus alpha L NFC. I calculated my result with 14 by 14 by 14 mesh for the VP and optimized A-word parameter. So the result for the coefficient alpha are listed in these two tables. The first table is for the FCC. We can see that the remove field method result has a very small deviation from the exact value. And say the old method has a big deviation for the M0 M0 term. Now it has a 10 to -7 deviation. So this method solved that problem. And this is the result for BCC. It has some similar accuracy as well. And I also plotted the potential for FCC and BCC structure. They show similar behavior to the Zhenhua model. So this is the plot for different part of the removed field method. The black line is the intra-cell contribution. The red line is the summation of the intra-cell contribution and the far multiple contribution. The far multiple contribution is given by this part, given by this term. And the near field correction term is given by the blue lines. So without this near field correction, we can see that it deviates heavily from the exact result. Similar thing is plotted for the BCC Morgan density. Oh, sorry, these are for the Zhenhua model, not Morgan density. I implemented the Poisson solver into a 4 potential KKR. When I solve the 4 potential KKR, I use Lippmann-Schwinkel equation to solve the regular wave function and the irregular wave function. The single-side matrix, single-side scattering matrix is obtained by this equation. The scattering path operator is obtained by this equation. Then we can construct the crystal Green's function by this equation. from the imaginary part of this Green's function gives the charge density, and then from charge density to solve the effective potential, then we can repeat this to until convergence. This is how I solve the full potential KKR. I tested my FPKR code with many results. This is the ground state for niobium system. I calculated 7 energy points and feed them to the equation of state. For systematic check, I also calculated for BCC and B2 like niobium. Both agrees pretty well. I also tested. I also calculated ground state for different BCC or FCC materials, and the result are listed in this table. This column is the LAPW F4 potential LAPW result for this material, or the lattice constant for this material, and then these two columns are the LDL results and PBE results separated by FPKR, and this column is the result by WASP. The result shows that FPKR is not bad. The last test for the full potential KKR is that I distorted the unit cell for a BCC system. This is a BCC niobium. I did 2 tests for 2 with different constraints. The first one is that I keep A2 equal to A3 equal to the ground state value, and it stretch the vector A1. So in this test, the volume is variable, and the result is shown in the black line. Another test is that I still keep A2 equal to A3, and I also keep the volume of the unit cell invariant to be the ground state value. So the result is the energy is plotted by the gray line. In principle, the variable volume should have higher energy than the fixed volume, and my result shows that it agrees with the expectation. So this I just explained how I solve the Coulomb potential, and I showed my result for the full potential KKR. So if you have any question, please.
How about force?
Force, the force calculation is that I haven't finished for this part yet, for the debugging for this part yet, since there is a mesh problem, the R mesh problem, and that caused calculation jump.
Okay, for this last example, there is no force on the atoms.
That's right.
Yeah, no force for this one. It's just the energy.
So you got the force exactly right. The challenge has always been to take that central atom in the cube and just displace it to see what the forces
Yeah,
you would
for this test, I would say that for this test, it doesn't have the mesh problem. When we calculate force, say if we displace the atom, this could cause the R mesh to be how to say it, the R mesh to be unstable, and it can cause trouble for the force calculation.
Okay, are you talking about the radial R mesh, like in the?
Yeah, the radial R mesh.
Okay, so in other words, the result is very sensitive to the gridding and the angular momentum cutoffs and so forth as you just try to displace an atom to get forces. That's what my takeaway.
Yes. I'm still debugging the code, so for that problem, it bothers me. I'm sure that it's not because of the Poisson solver, but I discussed that with somebody that is having a good answer so far. Why the R mesh has the problem?
Okay, back to the Lmax. So the Lmax is for the child density expansion, right?
Yes. The Lmax is charge density expansion. I also use Lmax for the potential as well. Currently, in my FPKR calculation, I only calculated charge density and the potential up to Lmax equal to 4. I tested the result with Lmax equal to 6 and Lmax equal to 4. It doesn't change much, but it needs more resource to do the calculation. So I only list the result for Lmax equal to 4 here.
But since your testing shows that you need a Lmax equal to 8 in order to get
yes, for this analytic model, you either need Lmax equal to 8 to get the exact agreement.
Another question is, you have the Lmax, the Lmax for the A sub L. Can it be different from the Lmax for child density?
For that, I use the same Lmax. I use the same Lmax for AL, alpha AL, and the charge density.
Okay, one of the big problems with the angular momentum comes in from those near field corrections and the shape of the cell, because it's not, it doesn't, the shape function does not converge very rapidly in L. But for the Poisson equation, it has this great property that it's a linear equation. You can break the charge up any way you want to, and you can use smooth cell functions that converge more rapidly in L. And I think angular momentum, the L expansion convergence, at least in the Poisson equation, will sort of go away. So I think what you've done, or or what Dwayne had done, or what I had done with Bill Shelton, depended on the specific cell shapes, whereas we could have gone to a smoother cell shape and avoided a lot of the angular momentum truncation problems.
Yeah. For this one, I would say that this near field correction term serves as a cancellation for the for this intra-cell contribution. When we calculate the intra-cell contribution, this term is calculated by the extended charge density. So it means that we have contribution from the charge density outside of the VP. And this near field correction serves as a removal to that part.
Okay, but you have let's see, where's this cell shape come in? It comes in through S of omega, right?
Yeah, this S is the surface of the VP surface. It's the surface of the VP.
Yeah, so that's the source of the angular momentum truncation problems right there. But I'm saying it's not essential to solving the problem.
Yes, in my calculation, I don't do this. I use the isoparametric method to calculate this integral.
Okay.
So this is the 3D integral. Inside the inscribed sphere, this part can be done differently. But from the inscribed sphere to the VP boundary, this contribution should be calculated differently.
Yeah, so in that case, you trade an angular momentum convergence problem with a grid convergence problem for your with the parametric integration.
Oh, okay. So this may be the problem of my first calculation.
Well, possibly. I think everything is very sensitive, and one of my recent interests or long-standing interests is trying to figure out how to make it less sensitive, just by the making sort of everything as stationary and as robust as it possibly can be. But the Poisson equation is particularly easy because it's a linear equation, and you can get rid of any abrupt changes like going through a cell shape surface. The Schrodinger equation is a little tougher.
Yeah, honestly speaking, this is not my perfect solution as well.
Okay.
I'm trying to develop a better one. The problem is that the funding has been cut.
Yeah,
So,
yeah, that's always a problem. And Yang has worked on a Fourier transform method.
Let me say something about, for those who are not in this field. VP means volatile polyhedron. Here, this on this picture, these squares are volatile polyhedron, which contains each atom. So that volatile polyhedron fill up the whole space. So that space divided by into volatile polyhedrons. But to solve the this Poisson equation, the way they do that, so they draw a kind of big sphere around each volatile polyhedron. They use like a multiple moment method to solve it. But thing is, there's an overlap, so that needs to be corrected. So-called near field correction is try to correct those overlaps.
yes.
Yeah. Okay. So then they have this integration. This S omega means it's from the surface of the volatile polyhedron up to the bounding sphere. So that's very strange volume integration. So they have developed this very unique method. Whatever what's the name? What's the ISO
integration?
Okay, yeah, they have another way to do that is you do the volume integration over the entire sphere, subtract the step function volume integration. You know, we have the step function, right? Just it's 1 inside the volatile polyhedron, 0 outside. So you can do a do subtraction. The difference is also, you basically do this. We can use the step function method to do this in volume integration.
Yes.
Yeah, the way I solve this Poisson equation is by dividing the charge density into 2 pieces. One piece is confined within non-overlapping spheres. Each sphere contains 1 atom. Now I solve the multiple moment method for calculating the potential arising from this non-overlapping charge densities within each sphere. Then the other rest of the charge density is a kind of smooth varying charge density. That I use like a Fourier transform to get the potential. So then, because of this kind of electrostatic problem is a linear, so the 2 potential add together is the solution. That's how I solve this. It's the same as FLPW, right? That's they're pretty much the same idea, same thing, right?
Yeah.
Yeah. But the problem with the Fourier transform is I have to do back and forth between uniform grids and back onto the radial grid, which causing the calculation become highly expensive for large unit cells. But this method, you don't have this kind of problem. You just stick with a radial grid all the way. So that's the nice part about this.
I would like to ask something. I'm sorry, I got a little lost here. It's a little complicated, and I'm not really an expert enough to understand every detail. But one of my longstanding questions, I have a friend, NREL in Colorado, Mladen Stevanovic, who was earlier work with Alex Zunger, and they were interested in the old Madelung story that if you have ionic solids, Madelung said that we can replace extended charge densities with point charges. And that works very well for sodium chloride and for example, magnesium oxide. But I've talked to others, like, for example, Socrates Pantelidis, who at Vanderbilt, who's another DFT guy. He said that this Madelung method of point ion model, right, is completely wrong. And that the textbook sodium chloride example and so forth is completely wrong. He said, well, why did you say that? So if you do LDA, for example, for this band insulator, it's an ionic insulator, you'll find that the charge on sodium is, well, the sodium is stripped of the electrons of this extra electron, and then you just see the ionic charge, which is pretty localized. You can think of a point charge, but then the charge that's transferred to chlorine, half of it goes into the interstitial site, and it's not just sitting on the chlorine or magnesium oxide. The charge on the oxide is not actually on the oxygen; it's actually everywhere. And now the question that comes to mind, which I'm asking, I'm not saying I know the answer to this question. If you actually use DFT, if you calculate the ground state energy for different polymorphs of MgO, and compare the difference in energy between different crystalline configurations, you can calculate that with DFT accurately. And then if you use the electrostatic point charge model, you'll find that it works very well. There's a very small error, less than like a % error in the energy difference. So it says that the energy difference between structures is mostly electrostatic, but the point charge model should work well. And this is what Madelung said, basically. Now the question is, why does that work so well when the charge is really not sitting on an ion? It's actually spread all over, especially that charge that's transferred to oxygen. Now this. So we were discussing this with various people, including Wei Ku, for example, and well, what Wei Ku said is that maybe it's because that charge actually has a distribution, radial distribution, which is consistent with some you can expand it in cubic harmonics in the cubic crystal, and so then when you do multiple expansion in these cubic harmonics, there'll be many cancellations, and only basically the first term or the point charge term, the L equals 0 term, will survive, and everything else goes away, right? So this is very strange. It's not obvious that this has to be like that. In other words, in most ionic solids, the textbooks one, the charge is really not so localized. Madelung said, and all the chemists, they think it's actually point charges. Point charge model works very well. Now you can calculate as you're doing the full distribution function. And the question is, why does the point charge model work so well? It is a related question to the convergence of the multiple expansion, right? So does anyone have a feeling about, or is there some knowledge? I mean, I may be ignorant, but is there some knowledge? Why is it that point charge model works so well? And how can we actually learn about this from this kind of discussion as we are seeing today?
Well, I think the monopole moments work very well because you're usually talking about, say, a cubic system where, you've got multiple, and then your next moment is up there at L equals 4. And also all the higher multipoles converge very rapidly. So their contributions, there's no long range part. And the thing that the Madelung does capture is the long range electrostatics. That's very critical in a lot of ionic systems holding together. So it's got that going for it. I mean, it's got the logic of long range electrostatic contributions to the energy, and the multipoles for a cubic system tend to dominate. I think that's the underlying.
But is there like a review article showing it quantitatively how? Because the related question is that instead of doing a continuum calculation like this with DFT, you could do downfolding, and I say, well, in some kind of, if I use vanilla orbitals, then I'll have it's a much simpler. The electrostatic calculation is much simpler because your charge density can be expanded in terms which come only for few vanilla functions. And so the question is, can one actually, is there a body of knowledge about this, the convergence with respect to these corrections to point charges? Is there like a review article, a book? I'm asking out of ignorance.
I don't think so. And as a matter of fact, taking it's great DFT, and I think sort of the general approach is, we know all these equations that will give us the right answer.
Yeah.
And then it's another problem to pick them apart and separate out the different contributions.
Right, yeah. Well, you know, my background, I'm not a DFT guy. I teamed up with these people because they're experts, and I mostly worked on lattice models, including long range Coulomb. But you know, this is all lattice models, tight binding, simple stuff, right? Where one can focus on some other things. But now the question is, you know, how can we get simple models out of these complicated descriptions, right? That's a real question. What you're saying, right? How, you know, and that's kind of confusing in many cases, at least to me, you know.
I think the person whose work to look at is David Pettifer. If anybody's good at extracting a simple model out of the DFT and getting rules of thumb, look at David Pettifer.
Well, he passed away.
Well, his work is still there, though.
Yeah.
So could you maybe send in the chat maybe some the write the name, because I'm unfamiliar with that, so I could follow up and learn.
Well, Malcolm knows I probably can't spell Pettifer right, but maybe Malcolm, you'll put that in the chat.
Okay.
I'll try find reference.
Thank you. I would like, you know, I mean, these are interesting things in principle. This is not my specialty, but from this Stevanovic guy who worked with Zunger, it turns out that these ion static models, they were not studying just periodic solids. They were studying inverted spinels, where you split, where you can, at finite temperature, the atoms trade positions in a multi-lattice sublattice situation, and then you have a random position of ions, and you can repeat electrostatic. These are still electrostatic calculations, and from the point ion model, even in absence of perfect symmetry, the point ion model works beautifully and explains the entire thermodynamics of spinels. Now, why is that so? You know, it seems that these multiples, except for the first term, they always cancel, even not only in the symmetric case, but in more generally. And one would like to know, well, you know, if I have a point ion model, I actually did some work where you can go beyond the Hartree approximation and treat the Coulomb, the thermal fluctuations of the Coulomb potential much more accurately, which is important for things like Wigner crystallization, etc. So for lattice models, I have some analytical theory that can be very useful and goes much beyond Hartree. But the big question to me is why should I be use a lattice model, and why does it make sense? And I could never get to the bottom of this. So it's kind of annoying. Pettifor, okay. Pettifor. Thank you, Malcolm. I will look this up. I could sit down and with some colleagues do calculations, trying to do the expansions and study this mathematically. It's very complicated. I can spend years doing it, and I have a nagging feeling that someone already knows the answer to all these questions, and it's written somewhere, except I'm not aware of it. And that would be stupid for me to spend my years of work when someone else already figured this out, maybe 30 years ago or whatever, you know.
Okay. Other questions?
Yeah, have you, or do you plan to do anything where you're treating systems which are far away from these cubic crystals? So you get, you know, long, thin, and various weird shapes, and I guess it's even just drawing the Voronoi polyhedron is a problem. So have you looked into that at all, or do you?
I haven't tested that for other system yet.
And I guess the other one is, yeah, it doesn't matter. I'll come up with something for you. Yeah.
I mean, this.
Have you tried silicon?
Yeah, I was going to ask, is silicon? Have you tried silicon, which is the?
I have a result for silicon. I remember I tested for silicon, but it's not listed here.
Mm-hmm.
Yeah. I have a conversion result for silicon.
Yeah.
The result is that the gap for the silicon it's underestimated.
Mhm.
Of course. If not, I will be worried.
Yeah.
Yeah, for silicon, I mean, you use empty cells, and then the angular momentum is just cutoffs for the Voronoi polyhedra is just the same as for a cubic system.
Yeah, what I tested, I didn't use. I remember I didn't use empty spheres. I don't remember that, since this one was tested last year, at the beginning or last year, I think. So I don't remember the details. Sorry.
I can't even recall. Does anyone asked about forces? So you can relax systems. Say you have a high entropy alloy and it's nominally BCC or FCC, but in fact no atom actually sits on an FCC or BCC site. So every atom is distorted. That's a sort of an important set of problems where these kinds of methods would be methods of choice, basically.
Yeah, the force calculation. I'm still debugging that part.
Mhm.
Yeah. Also, I have an impression that for a compound, you have two different elements. Then the way you set up the Voronoi polyhedron is by putting the plane, not rather instead of in between, just in between two atoms, but you put it into a kind of valley or maxima of charge density, right? That's how you set up your Voronoi.
Yes, yes.
Okay.
The VP construction use the value points for the charge density. We calculated the charge density and check the value points and set the boundary at the value points.
Okay.
So the VP size is different for each atom if we have for different elements in the system.
So may I ask concerning this, where you put the plane? So you're talking, I assume, about crystals, periodic crystals, right?
Yeah.
But you may wonder, if I have an alloy where I'm randomly mixing these elements, is this, so it has to do with the atomic radius, I guess, right? So in an alloy, is this Voronoi construction going to be, well, so, there's a line connecting two atoms, two centers of atoms. Then I can put a plane somewhere. You said it's not in the middle, but it respects somehow the atomic radius or the minimum of, of something. Now, if you have a random environment, can we still use the same point? Is this dramatically the choice where you put it? Is this dramatically affected by the perfect symmetry of the crystal, or in an alloy we could still use the same prescription which we established in a crystal?
You can use the same prescription.
For the alloy, we still use the value points to construct the VP. In general, a simple VP construction is that we can use the Wigner size way. We just we set up the boundary at the middle of two sides. The connection of the connection of the middle. Oh, sorry, the middle of the connection. To say that's the simple choice. But if we pick up with the value points of the density, this could better describe the system.
Well, so I think you can say it in the language of chemists. Atoms don't have the same radius, right? So obviously, the atomic radius. I mean, the distance between two atoms is the sum of two atomic radii, but they are different. They're not the same because they are different atoms, and so then it shouldn't be in the middle. But on the other hand, if I think that this is just the atomic radius, chemists think that atomic radius is the same in an alloy in a crystal.
Yeah,
right.
For the alloy side, what I would say is that we use same bonding sphere radius for the atoms for the alloy side. But for the alloy side, we have a different different concentration for different element, right? For that part, the atomic sphere radius is different. That's true.
So you see, that's what Malcolm said, which was a good point, right? That you think that if I have an alloy, I can still use the same. I mean, the long range order or the crystalline, there is still a lattice which is periodic, but it's locally distorted, and that doesn't destroy the long range order of the lattice, but it's locally distorted, and that it's not so clear how you take that into account, right? With this, I mean, you can do supercell calculations. That's obviously going to be the automatic, but if you want to do something like CPA, well, then it's confusing, right? I think that's what Malcolm said, isn't that? Is that what Malcolm said?
The VP construction, we can still construct the VP boundary by the valley point, right?
So that means each iteration you have to update, because at each self-consistent iteration, that valley point could move.
If we that means that you are doing structural relaxation.
No, not necessarily. Even if you do not do an atomic sphere, each atom has fixed as an intrinsic atomic radius. But if you do a valley point, as SCF iteration goes, the valley point could change its location. So you have to reset up the your Voronoi polyhedron.
The thing is that the VP is fixed for the whole self-consistent calculation. They for the alloy side, they could have they have the same VP, but they have different. I remember they have different inscribed sphere radii. Yeah. That's what we change.
So Malcolm, is this structural relaxation in alloy? Is this a huge effect, or it is a correction that can be treated, say, in a linear response approximation or something?
Sorry, I didn't hear this part clearly.
I was going to ask Malcolm. He was mentioning about structural relaxation in alloy.
Yeah.
So I was wondering, is this generally a small effect which can be treated as a to linear order as a correction, or it can be a huge effect that has to be treated self-consistently?
Yeah, I guess huge is in the eye of the beholder, but certainly these high entropy alloys, when you relax them, the relaxations can be quite large, particularly, if you're doing calculations that involve elements in different rows of the whether just in each row, and you take those, and if you go just straight down, you can get large differences in the atomic radius because of just the way that they pack, and for the 3Ds, magnetism is so important. But then the atom size is variable, and it's certainly variable below different rows of the elements. And different systems behave differently in terms of how big then the correction is, and if they're from the same elements are from the same column, then you've got one thing, and if they're from different columns, you've got something else, where the relaxations can be larger and the effects can be larger. So for many of these systems, you can get away, since you also want to deal with the disorder, just use KKR CPA to do that. But for some of them, I'm trying to remember which particular elements did that, but basically, If you look at the density of states for them, that the do a KKR CPA calculation and you do a supercell calculation, and they both give basically the same answers, which is meaning that these little distortions don't matter. But then for some others, they do matter. So KKR CPA is not as useful as it otherwise would be. But that's a completely other problem to today's discussion.
Thank you.
I have a question for Zhenhua. Have you guys ever considered the full potential KKR CPA?
Sorry.
Have you guys ever thought about doing full potential KKR CPA?
Yeah. We actually for this part, the code is there. I haven't tested it yet. When I coded the full potential CPA. But this part I needs some test.
Okay. All right. If no questions, it's already take an hour now. So thanks everybody. We hopefully have some follow-up discussion. If you interested, we can send an email to Zhenhua and ask.
Yeah, okay. Oh, and it was great seeing you, Don.
Hi, Marcus. Yeah, I'm sorry you're sitting on the railroad tracks there, but yeah.
Oh, yeah, that's actually in Taiwan.
Okay.
Well,
Yeah, this has been great. I hope we have some more KKR Zoom meetings. It'd be fun.
Oh yeah,
Oh,
you're
yeah.
welcome. Yeah, we have actually we do have like every 2 weeks we have a like MUST meeting. MUST stands for multiple scattering theory.
Okay. Well, send me the invite.
Yes, we will invite you. Not a problem.
Okay, great.
Yeah, I'm very pleased that you come back. What to do?
One other thing you might be interested in, Don, is Balázs Utfalusi is going to visit us, and I guess it's right at the end of the month.
When is he beginning of February?
Yeah.
Last week of February, just before the March meeting. So it's the last week of February.
Yeah.
Okay, yeah, I'd love to see Balázs and Marcus and everybody, but we'll see how COVID's doing by then, but maybe it's safe to travel by then.
Yeah.
Yeah, that would be nice. Get with Balázs.
Yeah.
Okay. Zhenhua, so I already made a recording. So do you mind if I put it on YouTube or just only share among us? What do you think?
I don't mind.
Okay. All right.
Okay, bye everybody.